Welcome to Probability and Statistics. In this lecture video, we're going to talk about the central limit theorem with the means. So what we want to do in this lecture video is begin to talk about how can I find the probability or the area under the curve of our sampling distribution about the X bar. Alright, so this theorem right here is the same one as I showed y'all in lecture video 3.1. So the mean of the sampling distribution X bar will eventually become the population mean, and the standard deviation of the sampling distribution X bar will become sigma population standard deviation divided by square root of n. So what we want to do again, just like back in lecture video chapter 6, where we got to convert into a z-score. So if the sample size n is at least 30 or population is normally distributed, the standard score for a sampling mean, this is very important, for a sampling mean, is going to be given by this formula. So now, this is no longer just random variable x, because my random variable is become the random variable X bar, the sample means, because I'm taking lots and lots of sample. Alright, so they become random variable. So my random variable now is going to be my sampling mean minus the mean of the distribution divided by standard deviation of the distribution X bar, which, as you can put together, this sigma of X bar becomes population deviation divided by square root of n. Alright, so this is a little bit different formula compared to the original one that we saw. So in a minute I will go back and bring out the other one as well. Alright, so again, find the z-score, convert your particular sample mean into a z-score, and then we can find the area under the curve. Alright, so here is the formulas again. We can either look up the probability or the graphing calculator, either way. So let's give this a try, We're still doing the same thing as compared to chapter 6. It's just the variable is changing, so the formula changed slightly. So let's say a quality control expert at a live battery wants to test their new batteries. The design engineer claims that they have a standard deviation of 62 minutes with a mean life of 606 minutes. So what the 62 means, that's the standard deviation of the population. The mean life, 606 minutes, will be the population mean. So if the claim is true, in a sample of 99 batteries, so I'm taking a 99 battery sample, what is the probability that the mean, this one word changing how we go from chapter 6 to chapter 7, what's the probability that the mean battery life will be greater than 619? So the 619 minutes is referring to the mean battery life of the 99 batteries. So that means, so let's write down what we know. So that means our X bar, the sample mean that I need to convert into a z-score is 619, and this part want me to find greater than 619, because normally the mean is at 606. So when we take a sample of 99 batteries, what's the chance, what's the probability that those 99 battery samples will have a mean battery life greater than 619 minutes? Alright, the mean of the population is 606. Alright, standard deviation of the population is 62 minutes. Alright, so as you can recall in my formula, the mean of the sampling distribution X bar will eventually becomes the population mean. mean of the distribution will eventually become the population mean, which is still going to be 606. The standard deviation of the sampling distribution from the formula is always going to be the population standard deviation 62 divided by the square root of my sample size n, 99. Alright. So, if you look at what's going on in terms of a graph, right now, the mean of the population and the sampling distribution is at 606. Okay. Alright. The 619 is actually referring to the sampling distribution. So this whole entire x-axis is referring to sampling distribution x bar. Now I'm going to convert my 619 into a z-score. So that this mean will eventually become 0 under the z-axis. Alright, so let me just take a picture of this. Alright, so this is my formula. Now I'm keep not having my mind. So this z-score is gonna be x bar. What I'm trying to convert is a 619 minus the mean of the distribution 606 divided by, okay, standard deviation is 62 over square root of 99. Alright, 2 decimal place. So convert to z-score before I can put into the normal CDF. So here I'm going to put my numerator in a parenthesis. I want the calculator to figure that out. Then divided by, like the calculator figured this out down here. So I put them in the parenthesis. 619 minus 606. Close it. Divided by, open another one. 62 divided by square root of 99. Close the parenthesis for my square root. Close the parenthesis for my denominator. Because my square root gave me a parenthesis, so I gotta close it. 2.09. So, as you can, so now you probably begin to understand why we standardize it. We standardize, make them all into z-score so we can easily put in the calculator or look up in the table, because different problems have different mean and standard deviation. Okay, that's why we want to standardize it. Makes it a little bit easier. 2.09. Because you got to remember, before calculator was invented, the table already existed for the z-score. So people like to convert them into z-score, then look up the table. Now with a calculator being invented, it just makes things a little bit more accurate. So now I will do my normal CDF. What am I looking for here? What am I looking for? I think the problem says what? Greater than 619. So I'm looking for the area to the right of my 619. It'll be right here. So that means my lower bound got to be 2.09, comma, upper bound keep on going to infinity, 1e99, comma 0, comma 1. Let's see what that will become. Second distribute. Comma 0, comma 1. Alright, so the area to the right of that 619 0.0183. So that means there is about 1.8% chance, okay, that the battery, that the 99 sample battery will go greater than 619 minutes. Okay. So just like any batteries, DC battery has a lifetime. It only lasts for so long before we have to replace it, or to the point where we cannot charge it anymore. Those kind of batteries. Alrighty. So let's look at another one. Okay. The mean point obtained from an aptitude examination is 179 points. So this is the mean of the test, with a variance of 225. What is the probability that the mean of the sample, so we're talking about the mean of a sample, will be less than 175 points if 77 exams are sampled? The mean of the sample will be less than 175. Alright, so this 175 is what we're trying to convert. So that particular random variable mean sample will be less than 175. Alright, right now what do we know? Just like up here, the mean of the population is 179. The mean of the distribution of the sampling X bar will eventually be the same as the population mean, because if I take enough samples, eventually, okay, it will equal out to the population mean. Alright, my sample size N is 77. Now this time the problem does not give me a population standard deviation. It actually gives me a population variance. So if the variance is 225, that means the standard deviation of the population got to be square root of 225, which I think is 15. Alright, so the standard deviation of the sampling distribution will just be sigma divided by square root of n. So that will be 15 over square root of 15. Excuse me, 77. So rather than figure out what this is, I'm just gonna type it up. I'm just gonna put it in the calculator when I convert to z-score. So I'm gonna copy this. Okay, so what's going on right now is this amplitude exam. The mean of the sampling distribution X bar. The mean is right here in the middle, which is 179 points. Was a chance that the mean of the sample, 175, will be less than 175. So I'm looking for the area to the left. So this is the area I'm looking for. Alright, so let's convert our 175 into a z-score. So follow the formula. So take my X bar, 175, minus the mean, divided by sigma is 15. Right, over square root of 77, 2 decimal place. So I'm gonna type in 175 minus 179 in the calculator first, in the parenthesis, divided by parenthesis 15. Put the bottom in the parenthesis, divided by square root of 77. Close the parenthesis for my square root, close the parenthesis for my denominator. Negative 2.34. So this 175 under the Z standard score is negative 2.34. So I'm looking for the area to the left. So normal CDF. Keep on going left means keep on going to negative infinity. So that will be negative 1E99, comma, upper bound come all the way up to negative 2.34, comma 0, comma 1. Let's see what that is. So my probability 0.0096. So the probability, okay, what the answer is saying is the probability that the mean of the sample, the 77, what's the chance that out of that 77 sample I took, okay, the mean grades will be less than 175, which is almost 1%. Okay. Alrighty. I like this problem. It's about televisions. I leave my television on all the time, which is not good. Alright, the mean life of a television set is 119 months with a standard deviation of 13. So if a sample of 67 television is randomly selected, what's the probability that the sample mean will be differ from the true mean by less than 2 months? Oh, that's weird. Okay, we got to read this thing a little bit to show you how to read this thing. This thing is weird. Okay. If I scratch off the word less than right now, what is probability that the sample mean will be different from the true mean, which is 119 by 2 months? Different means different by 2 months. Okay, so if the sampling distribution of the X bar eventually will become the same as the 119, differ from 119 means differ by 2 months, means it can either be 2 months less, which is 117, or 2 months greater, which is 121. Is it? Yeah. Okay. So that's what that represents. Differ by 2 months. Give or take plus or minus 2 months. That's what it's saying. Now, if I put this word less than back, okay, what would be differ from the true mean by less than 2 months? And this is where it's weird. This is where the drawing comes in. Differ by less than 2 months. So differ than 2 months will either give me 121 or 117. Less than means area to the left. So area to the left, 117, is right here, right? But the area less than the 121, the area less than 121 will be, for 121, everything go to the left. Everything to the left. Even this part right here is less than 121. So what you see right now, the one that's in color green, is the overlapping areas. Because if I find an area to the left of 121, it will actually cover some of the area to the left of 117. So what the problem is saying is, okay, if you want to be less than 2 months to the left of 117 and 121, what you're really looking for is the area that is in between the 117 and 121. So this is the area in the middle, different by 2 months, that I'm looking for. Okay, I know the wording is very strange. So under the z-axis, I need to convert my mean 117 and my mean 121 into a z-score, so I can see what's the probability here. All right. So the mean of the population will eventually become mean of the sampling distribution, which is 119. All right. Standard deviation. Population standard deviation is 3. Sample 67. All right. I'm looking for in between 117 and 121. So the standard deviation of my X bar, all right, will just be the population standard deviation. Sorry, standard deviation is 13. Population standard deviation 13 divided by square root of my sample size 67. Okay, so we got 2 random variable X bar to convert. So let me bring my formula back again. So I'm gonna move all these guys up slightly. So I'm gonna do it down here, okay? 1 here, 1 here. So everything will be the same except, okay, what the X bar is. So one of them will be 117 minus the 119, which you know is going to be -2 divided by my sigma is 13 divided by square root of n. The other one will just be 121 minus, okay, so I'm going to type in this one time, okay, 117 minus 119 divided by parenthesis 13 divided by square root of 67. Close it, close it. Okay, -1.26. So this one right here, this 117 gotta be -1.26. Alright, since they're different by 2 months, so this one here gotta be the positive 1.26. Okay, so that's my z-score. So now, what the problem is really asking us to find is the area between these two. What's the probability that the sample mean will be different, differ from the 119 by 2 months? So it's asking the area in between. So that would be normal CDF. Okay, my lower bound got to be -1.26. Upper bound positive 1.26. Comma 0, comma 1. My area in between 0.7923. So what is the probability that will be different from 119 by 2 months? 79% chance it will be different. Okay. Alright. This is a very neat problem too. So basically this problem we just did is looking for area in between. Okay. We don't want where area to the right, area to the left. A production manager at the wall clock company wants to test a new wall clocks. The designer claimed they have a mean life of 15 years. The clock will last 15 years with a variance of 25. If that claim is true, in a simple 41 wall clock, what is the chance that the mean clock life will be different from the population mean by more than 0.4 years? So this time is more than, okay? This time is more than. Alright, so let's try this again. Alright, so the mean of the distribution will eventually becomes a population mean of x bar, which is 15 years. Alright, so this is 15 years right here. Random variable x bar. So I know this one is the hardest one for me to explain. If I take off the word more than again, what's the differ by the true mean by 0.4 years? So that means differ by 0.4 means more than 0.4. So that'll be 15.4 here. Differ by 0.4, that can be 15.4 or 14.6. Alright, this is crazy, okay? This is crazy. More than. I don't know. More than the 15.4 is the area to the right. That is easy to comprehend. Okay. This is more than the 15.4. What is more than 14.6? Guys, to realize I've been saying more than means area to the right, okay? But if from where the mean is, I take away, I chop this entire right side off, how am I going to do more than 14.6? More than 14.6 on this graph does not mean to the right of 14.6. Okay, it actually does not mean that. Will be differ from the population mean by more than 0.4 years. More than that, more. This is actually more on the left side of that. It's actually on the left side of that 14.6. That part right there is the more. That's kind of hard to comprehend, because our mind is being stuck with more than this area to the right. In this case, it's actually referring to the area to the left for the more than the one on the right, more than the one on the left. If you need to be more than the one on the left, that is actually need to be what? All this area to the left of the 14.6. It's very hard to explain that concept. I need to be more than the 15.4. I need to be more than the 14.6. Okay. So this problem wants me to find the two tails. Okay. Alright. Think about it, okay? Think about it. More than this bigger number, more than the other one. On the other side, you got to look at the two sides in a way, look at them separately. Okay? If it ends at 15, okay, more than that is more that direction. That direction is to the left. Okay? Alright, so again, I got two z-scores I gotta convert. Okay. Two random variable x bar I need to convert to z-score, and I need to find the area for the two tails. Alright, so let's try again, okay? The problem give me a variance 25, so that means the standard deviation sigma is 5. Sample size 41. Alright, so the standard deviation of the x bar is going to be 5. Population standard deviation divided by square root of that 41. So it's going to be 14.6 minus the mean of distribution, which is 15. So that will give me the 0.4, negative 0.4, divided by 5 over population standard deviation divided by square root of my sample size 41. Alright, so the other side will just be the 15.4 okay, minus the 15. So differ by 0.4 means to the right, to the left of that true mean by 0.4 distance. Okay, so more than that distance. Another way to think about more than that distance to the left, all that everybody to the left of it is more. Okay, more than the distance 0.4. From 15 to 15.4 is 0.4 distance. More than that is everybody to the right of that. Okay, that's the way how you think about it in a way. So parenthesis 14.6 minus the 15 divided by parenthesis 5 over square root of 41. Close it, the square root, close my 41. Close my denominator. Negative 0.51. So the z-score for 15.4 gotta be positive 0.51 then. So since the normal distribution, normal curve is symmetric, my two z-score, one is positive, one is negative, same number, so that means these two area in the two tails are the same. So when I do my normal CDF, if I can do the normal CDF from negative infinity, negative 1e99, all the way to my upper bound here, let's look at this area to the left. Negative 1e99 all the way up to negative 0.51. That will give me this area. Since this area is the same, we can just times everything by 2. Okay, that will give me the area of two tails together. So 2 times second distribute negative 1e99 comma negative 0.51 comma 0 comma 1. So that'll be 0.6101. Okay, that's the area of the two tails. Alright, so I know these last two problems is kind of strange wording, but This one is finding the area of the two-tailed, the other one is finding the area in between. Alright, so that will conclude our sampling distribution of the X bar. In the next lecture video, we're going to talk about the sampling distribution of something called the population proportion. Alright, thank you for watching.